Actually, uh, the last class we started discussing the origin of resistivity or resistance. Okay, so that's why we have left. Okay, so what I'll do, I'll just give you a short recap what we had done that day, but we could not finish this. Okay, derivation. We'll just see. First, I'll just let you. Okay, let me remind you that what is the actual reason or origin for the resistance or resistivity in a material. Okay, whether it is conductor or whether it is insulator or whether it is semiconductor, all of them actually has certain resistance. So today's today first we'll discuss origin of resistance or resistivity. Resistivity. Okay. Okay, so resistivity is the actually fundamental property, and resistance is the manifestation of resistivity. Okay, effect of that. So resistivity is denoted by rho. As I said, if we just think of a conductor, suppose we think of a conductor. That day I talked about uh, 3 electrons in conductor. There are 3 electrons in the conductor. So 3 electrons in the conductor. Okay. So what happens if you take a single atom, isolated atom? So you have positive nucleus and electrons will be actually orbiting around it, okay, or revolving around it. The outermost electron will be having least attraction by this nucleus or positive charge, okay. So because of that, this has a tendency to leave the atom itself or leave the nucleus itself, okay. But when you have an isolated atom, just simply it cannot leave the nucleus, okay, or the atom itself. It doesn't. So for this electron, the outermost electron, which is called valence electron. So this electron to leave, you need to supply certain energy. So suppose I have a solid conductor, okay, solid conductor, a piece of solid conductor. Suppose this is a rectangular shape conductor, and see in this conductor I have many atoms, okay, many atoms. At least I can say of the order of 10 to the power 23, the Avogadro number. Okay, this much I can say. Okay, so this is not a less number. This is the huge. Okay, so I can just see I can denote an atom with a positive sign here and 1 electron here. Like that I can denote, because all the electrons inside will be closely will be strongly attracted by nucleus. So as a whole they will like see as a whole they will act as a separate entity, okay, and this electron in a conductor which is nearly free, that will act as other entity, separate entity. And since if you just take 1 electron out, so effective positive charge of the atom will be increasing. So what I'll say, I can say this part as core, okay, ion core, positive ion core, and this I can say electron or free electron, okay. So any atom can be thought of positive ion core, which is heavy, because nucleus, at the nucleus hole the mass of the atom is concentrated, so this will be heavy. So generally they are at rest, okay, they are at rest. So this free electrons, so when, see, I can just denote this as positive core and 1 electron, okay. I have compact like closely spaced other atoms also, because this is a solid I have of the order of 10 to the power 23. That means more than 23, 10 to the power 23 atoms are there. Okay, so they will be very, very close to each other. So when you have one atom and another atom very close to each other, so they have certain interactions. Okay, they have certain interactions. Okay, some interactions like, see, both of them will be having repulsion, and then this nucleus will attract this one, okay, this electron, and this will be again attracted by the other nucleus. Like that, there are many interactions. Okay, due to multiple interactions, there, see, these electrons will be actually moving in this, okay, in this solid as nearly free or with a common potential. Okay, with a common potential that you will learn in your higher classes. That potential has been derived by Hartree-Fock, Dirac, and all those things are there. Okay, so see, these electrons, what they will do, see, these are positive ion core, and the electrons will be actually free from everyone. So if I have 23 atoms, 10 to the power 23 atoms, then I will have almost 10 to the power 23 electrons. Okay, electrons in this solid, and they are free to roam anywhere. Okay, they will not bound to the nucleus, they will not be bound to a particular atom, so they will be randomly uh, roaming around. And you can look here, so while they are moving freely, they have, see, they have to undergo collision with this heavy positive ions, isn't it, positive cores. They have to undergo collision. So suppose uh, I have I have see, you are just going with a scooty to like through the market like the through the road, and when you just enter a market like, see, Tinagar or somewhere, maybe, or you may not know Chennai exactly. So there is a like huge crowd. What will happen? Your velocity will be automatically decreased, right? You have to decrease. So this is called scattering. This is called scattering, or some hindrance will be there. So suppose one electron is just trying to move freely around this nucleus, but see, this solid, but what will happen? It will encounter, various collisions. Okay, multiple collisions, multiple collisions. So with what? Not only with positive ions, even you have other electrons also. Not only one electron, you have this electron which is moving, so it can encounter many collisions with the all other uh, positive ions, as well as other electrons also, so there are multiple collisions, okay, while moving inside the material. So this is the reason, these collisions. Okay, so what is the origin of resistivity or resistance? That is the collision.
Good evening,
Okay,
sir.
collision. Good evening, very good evening, Priyadarshini. Actually, I waited for you for some time, but because it became
Sir, it is
more than
raining today,
10
sir,
minutes,
so I
so
was
I had to
unable to
start. But
join.
it is, oh, is it? Okay. Anyway, but this is the recapitulation I am doing. Okay, I'm just recapitulating all the thing whatever I had discussed, more or less. So I had not started the real lessons for today. I'll start now. Okay. Yeah. So yes. So this is the reason. So multiple collision happens with the positive ion cores or with the other electrons. So that is the reason why you have resistivity or resistance in any material. But this resistance, value of resistance or resistivity, that depends on material to material. Today we'll learn there are three types of material. Okay. Okay, there are three types of material. One is conductor. Okay, conductor. Then you have insulator, and you have semiconductor. Okay, semiconductor. Okay, these three types of materials are there broadly. Okay, okay. So today we'll see how this mathematically we will show how this velocity of the electrons inside the material depends on these collisions. Okay, when you apply an electric field, what happens? Like how the current is, how do you get the current actually? Okay, what is the way the electrons are moving? So what I told, I had defined that net flow of net rate of the net flow of charge will give you the current, right? That day we had discussed that. So if I just think a conductor of cylindrical shape, a conductor of cylindrical shape, okay, cylindrical shape, and suppose this conductor, there was initially there was no electric field. So what will happen? Electrons will be moving randomly inside the material. Okay, suppose this is an electron, so it will move in this way. Okay, so before collision, after collision with the same velocity, it will move this way maybe, and then another after suffering another collision. Okay, so these are the collisions. Suppose after that collision, it may again go like this. Then after this collision, it may go like this. So it is very random. Okay, the velocity of the electron, because they are undergoing collisions, and these collisions are actually thought of elastic collision. So what happens in elastic collision? And see, elastic collision, it happens that the kinetic energy remains remains conserved. Okay, kinetic energy conserved. Okay, kinetic energy remains conserved. That means the kinetic energy before collision and after collision remains the same. Okay, remains the same. So this is the actual or the like one of the property of elastic collision. Kinetic energy remains conserved. Okay, and because of this elastic collision, see, I have a massive positive ion core. When my tiny electron, okay, go there with the velocity v, and then collide with this, almost like this is actually stationary at rest. So what will happen? It will actually rebound back with same velocity. With same velocity, it will rebound back with same velocity. Okay, that is minus v. Okay, so this is how before collision and after collision we are thinking that the velocity of the electron will be the same before collision and after collision. Okay, so this is one assumption. So whatever it is, but if the direction of the velocity, because velocity is a vector quantity, if the direction is random, then if you take the average, okay, suppose I have n number of electrons, okay, n number of electrons. So average of the velocity of all the electrons, okay, I goes from 0 to n. So this will be actually 0. The average is written like this, okay, like say v1 plus v2 plus v3 dot up to vn and divided by n, like that. So this is the thought format I have written. So this is average, this is called average velocity. So if you don't have any electric field applied, okay, that means your, see, electric field applied is 0 here. Then what happens? There is no net direction. Okay, no net direction, no net direction for electrons. Okay, for electrons to move. Okay, so see, but what we have told, that flow, net flow, actually we need to know net flow of charge. Net flow of charge will give you actually current. Okay, net flow of charges. Okay, and we have defined the current is actually dq. If suppose dq amount of charge, suppose I take an area normal to the see the direction of the electric field or direction of the velocity of the electrons. If the velocity of electron this way, or maybe the electric field is this way, so electron velocity will be in this way. So dq by dt, this is actually called the current. Okay, electric current. Now what we'll do, we'll just try to derive what is the velocity. See, see, I am telling that net flow of charge is required to get the current. Okay. Then how do, if you have a random velocity like this, how do you get net flow of charge? Actually, when you apply an electric field, okay, suppose again the same step I am taking. Suppose I am taking, okay, suppose I am taking one area A, okay, inside the conductor, which is perpendicular to the applied electric field, which is this direction. Okay, this should see area is actually normal to the direction of the electric field. Now I have applied electric field to this conductor. Okay, so what happens in this case? So this is my question. Now see, I'm just trying to see in at any time t, what will be the net velocity? Okay, net velocity. Okay, net velocity or average velocity, I'll say average velocity of the electrons when I apply electric field. First attempt, like first aim is that what is the velocity, average velocity, okay, of all the electrons in time at any time t. I am taking in number of electrons, right? So first let me take just ith electron. Okay, I'm just observing this ith electron how it moves. Okay, so suppose I have to see after time t what happened. I just think that the electron has undergone one collision t just before t time. Okay, just before t, exactly before t one collision it's already encountered, right? And see, before it goes to the second collision or the next collision, it said that consecutive, the velocity in between the consecutive collision, I'm going to calculate the velocity. Okay, velocity or average velocity in between the consecutive collision. This is one collision and the collision two. Suppose this collision already had occurred. Okay, after that this time t is, I'm just looking for a time interval. It's a total time t, suppose. Okay, so I have taken ith electron. Okay, ith electron, and suppose this ith electron elapsed time, ith electron elapsed time ti. Okay, ti before the next collision. Okay, next collision. What I'm trying to say, this collision already has occurred, collision 1. Just before this collision happened, the electron, ith electron, had actually passed time ti. Okay, ti time, suppose. Okay, now I had already applied electric field. So I am saying that now, since this electric field is already there, electric field is there means what? Electric field will exert a force on this electron also. So what is the force? That is E minus E into E. This is the force. That means if there is a force, then the electron will have certain acceleration, right? Acceleration. So what is that acceleration? That acceleration is actually, suppose if I say ith electron, for ith electron. So what is that acceleration? This is E by m, force by mass of the electron. Okay, so this is the acceleration it will have when during this ti time. Okay, during this ti time. So I can find out the velocity after t time or ti time, whatever you say. So this t time actually, in general, the total time phenomena. I'm just looking the phenomena for a duration of t time. Okay, duration of t time, and ti is the time. This ti is the time which this ith electron, that means one electron is taking. So you may ask me a question, sir, you have taken the ti time for ith electron, but what about the other electrons? Yes, actually all of them will not take the same time to same time between consecutive collisions. It may vary. It may vary. Okay, between a time tau. Okay, so t I plus one. Okay, so it may vary between one average time that will say. Okay, so this is for ith electron. So what will be the velocity of that guy? Okay, what will be the velocity of that electron then? Ith electron. So this will be velocity will be like, see, this is, suppose this is the average velocity I'm taking during that time, or suppose the velocity of first electron, ith electron itself. Okay, let me take the velocity of the ith electron after ti time. What will be that? So initially, suppose it has a velocity just after collision, which is a random velocity. Just after collision, that velocity will be random. That velocity, suppose vi, small vi I am writing here, small vi. If I write in terms of vector, I can write like this. Okay, but this velocity is actually random velocity. It does not have any direction. Okay, this is a random velocity. And see, I can just use my formula from kinematics. Okay, since it's constant acceleration or uniform acceleration, so the final velocity will be initial velocity plus 8 into t. Ti is the time, and okay, a is the acceleration, which is actually e, and plus, so because it is a minus sign here, acceleration, so I'm taking minus here by m. So this is the acceleration into ti. This is the velocity during, okay, so which time? During ti. Okay, or maybe you can say after ti time. This is the velocity of only one electron. So if I want to calculate the average velocity for like all the electrons, average velocity, so what I have to do for average velocity, I have to take the time average of that. So how do you get the time average? I'll tell you. And what is the value of that? I'll tell you. So, so the average velocity, okay. So this is even written as Vd also, Vd, drift velocity also. So this I can write average of this velocity, average of this. Okay. If I take average of this, that means what? Average of this velocity. Okay. I'm just writing as scalar only. Okay. Now this is E by M. See, average. So these are constant quantity. Charge of the electron is constant. Electric field I have taken constant, and M, mass of the electron, is constant. So see, I'm taking the average of time. You might be thinking, sir, why you are taking average of time? As I said, all the electrons will not suffer a collision, consecutive collision, okay, or not elapse the same time between two consecutive collisions. Okay, so some cases it will be ti, some cases it will be some tn. That means the time can be different for different electrons. Okay, so collision does not happen uh, that regular interval. Okay, that may vary from electron to electron. So that's why I have to take this average also. So see, this average I'm writing as V D D. That means the drift velocity. I'll let you know what is drift velocity is. So this is actually, see, this is a random velocity
Sir,
just after collision, right? This is random velocity. Yes. Yes. Okay. Who's that? Anybody is asking anything? Hello. Yeah. Can anybody respond to me whether you people are able to hear me properly or not? Are all of you able to hear me properly? Okay, I don't know. Okay, Nikhil is there. Okay, Kirtana, Shoma, okay, Shobari is also there. I think everybody is there. I hope. Are you all able to hear me? Can you just respond to me? Okay, nice. Okay, I have got the response from Mridula. Okay, nice. So let me continue. So see, look, this velocity is a random velocity, and if you take an average of any random quantity, that will give you zero. Okay. And see, this is constant term. I'll just keep as it is. And see, this T average I'm just writing as tau. So what is this tau called? This tau is actually called relaxation time. Relaxation time. So what I got? So I'll just erase all these things and then I'll write the final result what I got. See, I have got the velocity, average velocity of the electron as E by m into tau. This is the average velocity, and you can see this is not the time which I am talking about here. Actually, I was taking or I was calculating velocity at any time t or during any interval of time t. Okay, I was calculating in this time interval, but this time is not coming in this expression. Okay, so this time is different time. This time is actually, see, relaxation means what? Just suppose this collision already happened, and before it goes to like before the second collision happened, the time, average time, all the electrons elapse or relax before it collides. Okay, collide. That time is called actually the tau. Okay, that duration of the time is called tau. This is relaxation time. This is called relaxation time. Relaxation time. I hope you understood what is relaxation time. And this is actually average time, okay? Average of that. What does this mean? Average time is tau. That means what? See, all the electron. I have maybe some, as I said, n. Suppose n electrons. So suppose ith electron will collide after ti second, and the other electron will collide after maybe t I plus 1 second. Okay, like that. It can see the time taken by all the electrons will not be same. Some of them can take less than pi, some of them collide in time greater than ti. So because of that, this t average has been taken. Actually, these are all statistical phenomena. Okay, all statistical phenomena you will learn in your higher classes of physics study. Okay, statistical phenomena. So that's why always you need to take average and all those things. And this average, because all the electrons are not have not undergoing collision identically. Okay, not identically happening. That's why average things are taken here. Okay, so this velocity is called drift velocity. Okay, this Vd is called drift velocity. You can see this drift velocity has certain properties. What are those properties? See, this drift velocity is an average velocity. This is an average velocity. Okay, even though electrons are getting accelerated, but this velocity is actually average velocity, an average velocity. It is very peculiar, right? The object is moving, having acceleration. Okay, it is having acceleration, but moving with average velocity. That is because of the collision. That is because of the collision. Okay. So this is drift velocity, and it is time independent. See, there is no time involved in this, or yeah, no time arising in this expression. So this is called drift velocity. So we have got the expression for drift velocity then. Okay, drift velocity is E small e into capital E. This is the electric field, and this is a vector. If I write in terms of vector, look, the velocity. See, if I draw the cylinder again like this, okay. See, my electric field is this direction. Okay, suppose this is the area perpendicular to the electric field I have taken. Okay, in this conductor. Now, since the electric field is okay, electric field is this direction. So, see, the electrons will move in this direction with Vd. Okay, with Vd. With Vd, they will move in this direction, opposite to the electric field direction. Okay, opposite to the direction of the electric field. Okay, very nice. I have to find out expression for current. Okay, expression for current or current density. That day we had discussed current density. Current density means I by A. Okay, so the current per unit area. So this is the area I have taken. Okay, so to get the current density, what I have to find out? I have to find out current first. So what I am thinking that, say I have already got the velocity of the electrons. So this is the net velocity or average velocity with which the electrons are moving. So that means, see, they will actually cross this area. So I'll just take that, I'll just think that delta t time, I'll just see how many electrons are crossing this area. How many electrons are crossing this area. Okay. Okay. So suppose the, see, n is the number density or number of electrons per unit volume. Okay, per unit volume. So this is the per unit volume. So see, since this is the velocity, so in delta t time, what will be the length that electron will be actually crossing? Suppose in this direction, in delta t time. Okay, if suppose this is the length L, so this is delta t time after delta t time interval. So suppose they reach this, okay, this place. So this is the actually length. What is this length? This length I can get as Vd into delta t. Do you agree with me? This is the length of or the distance this electron travel in delta t time. Okay. Now see, I have, see, if you want to find out how many electrons are, see, I can get current by writing dq by dt, right? Dq by dt. So I need to know that in dt time how many electrons or how many charges have actually crossed. Okay, how many charges had flown, like flown, or yeah. So how many charges went through this area? If I can find out that number, then I can divide with that, like how many. Okay, so if I know the number, then I can multiply with e, so I'll get the total charge flowing, okay, in delta t time. If I know total charge flowing in delta t time, then I can find out this current. Okay, so let us see how can I do. See, the electrons, number of electrons will be, see, total number of electrons which are flowing or, yeah, moving in delta t time or crossing this area in delta t time will be, see, the area under this. Okay, sorry, volume into this. Okay, so the electrons which are crossing this volume. Okay, this volume, that means this is my cylinder, small cylinder, which has a length vd into delta t. Okay, and this has area of cross section a. So what is the volume here? So the number of electrons which are there in this volume are crossing in this delta time. Okay, so let me get the total number. Suppose this n is actually, so this is the number per unit volume. So I can get number of charge per unit volume into the volume. So this will be the total charge, okay, which are flowing in delta t time or or crossing this area. Okay, so this is the total number. This is the total number of electrons. So if I want to know what is the total charge dq in delta t time, so what I have to say, see, I am taking negative sign for electronic charge, and these many electrons are there. So this is the total charge. Do you agree with me or not? Okay, so then you get minus n into e v d area into delta t. So this is the total charge flowing or crossing this area perpendicular to the electric field, and that too in the opposite direction, obviously, in delta t time. Okay, okay. So I'll just remove some of this part, and then, okay, let me tell you once again. So I have to find out the total charge which is crossing across this area, which is perpendicular to the electric field in time delta t. How can you get? We can get, if I know, say, I know number of charge per unit volume. per unit volume I know, number of electrons per unit volume I know, so that is small n. So if I want to know the total number of charge, so I can get the volume, okay, and multiply, then I get the total number, which I have done here. Because this delta t time, what is the volume in that time? This is the volume of the cylinder, this small cylinder which I have drawn freshly here. Okay, this is the volume. So in this volume, the total number of electrons will actually cross this area in delta t time. So that is what I have written. And from the definition of the current also I can get the total charge. Okay, that is I into delta t. If my current flowing is I, okay, if my current is flowing, current always flows, okay, in the opposite direction of the electron flow. Electrons are flowing in this direction, okay, and current is flowing along with the electric field. Okay, so this is my total charge. So this I can just equate, right? These two I can equate. Look, I can equate this, that I into delta t is equal to this delta q, what I have got. What I have got, n, small n into E into V into D A delta t, right? I have got this. Now I'll just erase this part. So this part is very important. Actually, this derivation comes in your exam. Okay. So better you understand now. If you have any doubt, you can ask me. So the delta tau, delta t goes like I can cross it. So see, I can write this as J, because this is I by A. I can write I by A because this A I will bring this side. So this I can write as N E V D. Okay. Look, current is actually, see, current is actually a scalar quantity that I was telling. See, it has direction, it has magnitude, but it does not. Okay, current does not follow the rules of vector addition. Okay, that's why that's why I is scalar. Okay, current is scalar. Okay, that day I think there was some doubt, okay, among you. So this is why it is scalar. It has, even though it has direction and it has magnitude, but still it is a scalar quantity because it does not follow, okay, it does not follow the rules of vector addition. That is why it is a scalar quantity. But look, when I will be writing the current density is a vector quantity. You might be thinking, how is it possible? Look the expression, what I have written here. This is the current density expression. You look in the right hand side, you look right hand side, this is a velocity. This is drift velocity. So velocity is a vector, okay. And you have already learned that if in a equation one side is vector, the other side must be a vector quantity. So I can write this is a vector quantity, okay. This is a vector quantity, okay, because this Vd is vector quantity. Okay, I think okay, fine, yeah, this is actually current density. Okay, this is the expression I have got now, right? So my, now I can do one thing, I can just go with, see, I know, okay, I'll let me do one thing, I'll just write down the, see, I'll just substitute the value of Vd and see what I get. I'll just erase this part, or I'll erase everything first. Okay, so what we have got, current density is equal to n into Vd. This is a velocity vector. So that's why current density is actually a vector. See, what is current density actually? You know, current density is, suppose this area, okay, this area. So area always has a vector. You know, like this is an area. This is a vector. How do you find out the vector? Vector will be actually outward normal, this way or this way, anything. If you just keep it vertically, so in both direction you can write your vector normal. So okay, if this is n, you write n, this is minus n, okay, like that. Okay, so suppose I have like area like this, I have vector normal, say normal to this area is the direction, okay, this is the direction of this area vector, okay. area. I can write this A in cap. This is area vector. Okay, I can write like this. So area has a direction, that is directional vector. Yeah. So yeah. So you can understand that why this current density is actually, you have to somewhat visualize. See, this current density actually always goes normal to the surface. Okay, outwardly normal. Okay, that's why. And also you look here what I have written in this expression. It is actually Vd in the right hand side, so the which is a vector quantity. That's why current density is vector, and it has unit. What is the unit of current density? So it is I by A. That means ampere per meter square. Okay, ampere per meter square. This is the unit current density. Okay, SI unit obviously. Now look what I'll do. I have got this value Vd is equal to E by m into tau. I'll just substitute here and then see what I get. I'll write here itself. So minus minus goes off. N into E square 1 E here. Okay. Then you get uh, this capital E tau by m. All right. See, J is equal to this, and this is electric field. So now I'll just for my convenience, I'll write in terms of scalar quantity itself. Okay, scalar notation. I'll write like this: J is equal to, see, this N is square E. Okay, so N square tau by m. Okay, I'll just keep it in bracket, and this is my E. So look, I had actually derived one expression. Do you remember the last day? Ohm's law in like new form. J is equal to current density is equal to sigma into E. Sigma into E. What is this sigma? Sigma is actually conductivity. I hope you remember. If not, you just go back to your like go back and read. You'll see this was Ohm's law. Okay, Ohm's law. Okay, if we compare these two equations, this suppose one and this is equation two. If you compare this, what is the value of sigma? Sigma is actually, or conductivity actually is given by n square tau by n. So this is the expression for conductivity. Actually, you may be getting a question on this. You need to remember these values. Okay. Sometimes they will ask you the dimension of this, or maybe they can ask you find out the expression for this conductivity. Okay. Whatever derivation I have done, you have to do all the way, all those things, and nicely written in your book. Okay. So you have to. So if you don't understand whatever I have taught so far, you can ask me, or uh, if everything is okay, then I'll just move forward. Is everything okay for all of you so far? Okay. So hope everything okay. Then I'll. Oh, fine. Okay. So I'll just move on. See, now look what we are going to learn now. So this we have already covered. Okay. So this is all the way we have derived. So this is the thing we have derived now, current density. Look, this is n square by m into tau. This is called conductivity. Okay. Now see, as you have conductivity, how we get conductivity? Because of the motion of the charge, or yeah, so motion, or because of the mobile charges. Okay. You look here, it is written. So conductivity arises from mobile charges. Okay. So like, since this mobility for the charges has come due to what? Due to applied electric field. But suppose I have been given a material. See, this conductivity or mobility or whatever, this depends on the material. It depends on the materials, okay? Because in various materials, the nature of the electrons, whether they will be free, nearly free, or not at all free, that depends on the material to material, and also it depends on how much electric field you have given. So the drift velocity depends on, see, as you have seen, the drift velocity depends on electric field. Okay, drift velocity, as you can see from here, the drift velocity, this expression, you can see that this is the expression for the drift velocity. The drift velocity depends on, and it is proportional to the electric field. So for any material, what will be the possibility of movement of the electron? So that you can express with a nice term that is called mobility. Mobility of electrons in any material. How do we define that? This is actually drift velocity per unit applied electric field. So this, see, sometime you may get a question, maybe short type question, 1 marks. So what is called mobility of an electron? So that will be another question. Okay. So okay. So what is mobility of electrons? So that is defined as drift velocity. Okay, drift velocity per unit electric field, applied electric field. So if you want to find out what is mobility, see, I know drift velocity is et. If I take the magnitude, okay, magnitude modulus, so e into e by m into tau. So this is the drift velocity expression for the drift velocity, and I know what is electric. Okay, so if you just divide with electric field, you get, what you get is e into tau by m. Okay, e into tau by m. So this is your mobility. So sometimes they will ask you to find out the dimension of the mobility or unit of the mobility or expression. You have to write down the expression for the mobility. So you need to kind of like remember logically. Okay. So this is called mobility of the electrons, and depending on that, you get the current or you get the conductivity, etc. Okay. You get conductivity, etc. Depending on the mobility. What is the mobility or probability of having motion, okay, for electrons? Okay, now we'll learn one interesting thing, that limitations of Ohm's law. Limitations of, so this I'm not writing because these are kind of philosophical things. Okay, there are no much derivations in this, and there are nice figures also here. So I'll just continue with this. Uh, okay, with this itself. Okay, look, uh, see, limitations of Ohm's law. So what we have learned, that V and I, they are directly proportional according to Ohm's law. Okay, let me just write a short note. First, let me remind you what is Ohm's law. Then I'll tell you the flaws in the Ohm's law. So Ohm's law states actually that V is proportional to I, or vice versa. Okay. So then proportionality constant, you have got R, and you got an equation V is equal to IR. Okay. If you plot V and I, so you get a straight line curve which okay, which goes to the origin. Okay, goes to the origin. So this is actually Ohm's law, where we say V is proportional to I. That means for a particular velocity, a particular voltage or potential, you get a particular current. Okay, particular current you get. Okay, this is Ohm's law. Now look in a book that there are materials which actually does not obey Ohm's law. Okay, or some conditions are there, some situations, at some situations the Ohm's law will deviate. Okay, the material will deviate from its Ohm's law. Okay, look here in this case, the dotted curve in this figure 3.5, the dotted line is actually for the original Ohm's law, but this blue curve, what you can see, this is the deviation. That means at very high current and very high voltage, this voltage and current, they no longer becomes proportional to each other. Okay, they no longer becomes proportional to each other. That means there is non-linearity here. Okay, at very high voltage and very high current, some cases. So I can tell you another situation where current and voltage will not be proportional to each other. Where, see, I have certain materials. If you apply electric voltage in the suppose forward direction or positive direction. Okay, so look at this figure 3.6. In this case, look here, the current and voltage are not proportionally increasing, right? Not proportionally increasing. Okay, see, after certain critical voltage, this is increasing like anything. Okay, so this is not a proportionality, so it would have gone through the origin if Ohm's law is obeyed, but it is not. That means Ohm's law is not valid here. Okay, and look here, if I apply the same, see, on the same material, I apply the same voltage but in the opposite direction with opposite polarity. With opposite polarity, what happens? See, that is called reverse polarity. So in the reverse polarity, look, this current, the value of current, you look here, how much it is? Almost 1.5. See, this is so large value, but you look here, this is very small value of the current you get. And obviously in this way also, the voltage and current, they are not in the reverse direction also, they are not varying linearly. Okay, this happens in case of diode, semiconductor diode. Okay, this happens in case of semiconductor diode. In the forward biasing condition, you can get this way current. After certain threshold voltage, you get to see current. Okay, and after certain critical voltage, the current will be increasing like anything. Okay, and in the reverse case also the same thing happens. Current will be, but current in the reverse direction and the forward direction magnitude will be differing like anything. So in this case, forward case you will get milliampere order, and see, in the reverse direction you are getting microampere order current for the same voltage. That means voltage and current does not have linear relationship, or they are no longer proportional to each other in case of semiconductor diode. And that's why this kind of, see, the device which are made of semiconductor diode are called non-linear device. Non-linear device. And the devices which are actually following Ohm's law are called linear devices in electronics. Okay. Okay. So this is a deviation. See, another situation we can get where for different values of voltage you may get the same current. You look here, this figure, maybe I'll just take this figure and explain. Okay, as I started at 610, maybe I'll go up to 610 and 710. Okay, please be patient. Okay, so look, some cases you look for a different value of voltage. See, this is suppose V1. Okay, or I take some other, maybe this one. So this is one voltage, suppose V. Okay, this is V1, and another voltage, suppose here V2. Okay, see, almost same current you get here, right? Almost same current, but do two different values of voltage, you are getting same current. My drawing is not proper horizontal. If this line is horizontal, then these two values are same, values of current are same. That means what? V is no longer proportional to I. And even for the current does not have unique value. No unique current is obtained here. No unique current. You are not getting unique current. Okay, unique current for voltage. Okay, so this is how, and this happens actually GaAs. That means gallium arsenide. This is also semiconducting material. Okay, semiconducting material. Okay, so yeah, now, so you can see that there is a deviation of Ohm's law. So there are the situations where, so see, there will be some multiple choice type question, or maybe some short answer type question, like give an example. Okay, where Ohm's law is not valid. Okay, you have to write semiconductor. Okay, you have to write semiconductor devices. Okay, in that case. Now see, resistivity of material, for different materials, this resistivity will be different. For conductor, which has actually good mobility is very high. That means electrons will, and in conductors are actually they have free electrons, but insulators and all, see, they don't have free electrons. That means, see what I showed in the beginning, that in case of metal, the electrons are no longer in the material, okay, in the material. So I have positive ion core and electrons. Okay, in case of insulator, what happens? Insulators, even though they are coming very close to each other, okay, even though they have interaction, but still these electrons, valence electrons, will keep their identity, with their respective atom, okay, respective atom. They will not leave the atom and roam around, okay, they will not roam around, okay, they will just be there, strongly bound with their respective nucleus or core. That's why they don't have free electron. No free electron you will get in case of insulator. No free electrons, okay. This we have learned already. Dielectric part we have already discussed, okay. Polarized and dielectric. See, if you apply very high electric field, what happens in this case? The positive ion core will be going in this way, and negative charges will be coming. Negative charge centers will be like this, in this way, okay. In fact, they will not be separated that much, okay. See what happens. And in the middle actually there will be no charge, okay. In the middle there will be no charges, okay. Why? I have shown you that, see what happened, only negative charges and positive charges centers, they will be displaced little bit, otherwise they coincide each other, okay, and net charge becomes zero. But in this case, there is a separation between positive charge center and negative charge center, okay. And like, see, other atom also will be here, positive this side negative, and the other one is like this, positive here, negative here, because electric field is in this way, okay. So look, this guy will combine each other, these two will combine each other and make each other neutral. Again, these two will make each other neutral. So you will get, at the end you will get positive and negative charges like this, okay. So for insulator, then the resistivity will be very large. It will be of the order of 10 to the power 18 ohm centimeter, okay, ohm centimeter, ohm centimeter, okay. And in case of conductor, it will be, for conductor it will be of the order of 10 to the power -8 to 10 to the power -6 ohm centimeter, okay. And in case of insulator, this is more, this may be 10 to the power 18 or more than that. And there are some other kind of material which I have already told, that is semiconductor, which have conductivity, sorry, resistivity in between them, semiconductors, okay. So you have resistivity. See, semiconductor, this way actually conductor, it is got greater than conductor, okay, rho conductor, okay, but less than rho insulator. Resistivity for semiconductors will be intermediate, okay. And one more interesting thing is that for a semiconductor, see, I have seen, see, in case of conductor, what happens, they have free electrons. So if I increase the temperature, what happens, I am giving average more energy to the electrons, to move with more velocity, increased velocity. So what will happen, I have cores, okay, I have all positive cores here. So if I give more energy to the electrons, it will move, and probability of collision will be, it will move with more velocity. So probability of collision, okay, probability of collision increases. Increases? Probability of collision increases for a conductor. Upon heating, that means what, if you heat a conductor, its resistivity increases and conductivity decreases. That means you will get less current, or resistance will be more, in other words, if you increase the temperature of a conductor. But what happens to the insulator and semiconductor? Both, in case of insulator or semiconductor, the resistance decreases. Okay, because more and more electrons which are bound, if you give more thermal energy, so these bound electrons will be making themselves free. So you will see, if you increase in an insulator, if you increase the temperature or semiconductor, both cases, what happens, as you increase your temperature, number of charge carriers increases, okay, which will carry the current. That's why your current increases, that means resistivity decreases, okay, because more and more charge carriers are coming for carrying your uh, electricity, okay. So resistivity decreases like this, okay, for a semiconductor. If you increase the temperature, the resistivity or resistance, you can write, so that decreases like this, okay, because more and more charges will be arising for conduction of current, okay. So I think with this I'll just stop today's class here, okay. I don't know how many of you are here, so many has left already, okay. So I'll stop it here, because this derivation was important. I just spent a lot of time over there. So next day onwards we'll just try to move faster, and you just read up to this portion, okay, why a semiconductor, like how the resistance or resistivity changes with temperature for semiconductor, conductor, and all those things. So with this I'll stop today's class. Next day I think we are meeting on Wednesday, okay. Okay then, yeah.